We spent a couple of days leading up to our test talking about uniform circular motion. What does that word uniform mean? Consistent, constant. Specifically, in this case, we're talking about a constant speed. Objects going around in a circle, traveling at a constant speed. Now, there's three terms that we addressed here. We've reviewed these a couple times already, so they should go pretty quickly for us. What was frequency? The number of rotations per unit time. The symbol for frequency was a lowercase f. It's not capital F because that would be force. Lowercase f is the number of cycles per unit time. So we're going to create a little equation for that. It's the number of cycles over the time. What are the units for frequency? Hertz. You could say cycles per second. 1 cycle per second is the same thing as 1 hertz. All right. The period. Period is kind of the opposite, right, of frequency. If frequency is the number of cycles per unit time, then the period, as given by the symbol capital T, is the time per cycle. So we're going to write an equation for that, time over the number of cycles. It's the exact opposite, right? The units for this, for period, would be... No, RPMs would be a unit for frequency, right? Revolutions per minute. It's not the standard unit, but it would still be a unit for frequency. The unit for this would be, yeah, usually we just say seconds. Like technically it's seconds per cycle, but usually we just say seconds. What's the equation that relates the two of these together? Frequency and period. This is the one that does appear on my data sheet. Yeah, T is equal to 1 over F. And of course, we can rearrange that to solve for frequency. It becomes 1 over T. Now, speed isn't really a new term for us, but the equation that we see for speed is a pretty new equation for us. We know that the object going in uniform circular motion is traveling at a constant speed. So we're going to say that it's represented by d over t. But we know the distance around a circle one time is called the circumference. Yeah, and what's the equation for the circumference? 2 pi r. And what's the time around the circle one time? It's the period, which is capital T. So we're going to say 2 pi r over t. This also appears on our data sheet, 2 pi r over t. All right. We had a few questions that we were working on the other day on page 250. Any issues with any of those three questions on page 250? Nick, can we do, sorry, 1 and 2? 1, 2, and 3? Okay, we'll do all three of them. Number 1 says the propeller of a toy airplane rotates at 300. What is this RPM? What does RPM stand for? Revolutions per minute. We don't want that, do we? Hey, that's not a standard unit. What's the standard unit that we want to use? So we're talking about frequency then, right? If you're saying it's hertz, we're talking about frequency. In fact, that's what we want to do is find its frequency in hertz. If we have 300 RPM, then how do we get RPS, revolutions per second, or hertz? Yep. Yeah. Yeah, let's divide it by 60. If you get 300 in a minute, then you get 1/60th of that in a second. You divide that by 60 and you end up getting 5, I think it is, isn't it? 5.00 RPS, or revs per second, or hertz. Is that a reasonable number? Well, if it makes 5 rotations in 1 second, it's going to make more than that in 1 minute. So that works. An electric motor rotates at a frequency of 40 hertz. What's the rotational frequency in RPM? It's backwards, isn't it? Here's our frequency in hertz. 40 revolutions per second now. We want to find the number of revolutions per minute. What are we going to do? Now we're going to multiply it by 60. We should end up with a bigger number. Of course, you get more revolutions in a minute than you do in a second. 4 times 6 is 24. Tack on 2 zeros. And we get 2,400 RPMs. How many digits should that be? 2 digits. So we're going to make it 2.4 times 10 to the 3 RPM. And finally, number 3 says a medical centrifuge is a device that separates blood into its parts. You ever heard of a centrifuge before? Where have you heard it? Where have you heard that word?
Some roller coasters named after it.
Okay. A centrifuge is anything really that spins around. Okay, and a lot of times what a centrifuge is designed to do is to separate things. The more inertia something has, the more likely it is to go to the outside of the circle. So in other words, the heavier something is, the more likely it is to go to the outside of the circle. If you put blood into a special test tube, and it has to be a special test tube, because if it's just a regular chemistry test tube, it'll break. It'll shatter in the centrifuge. This special test tube that's designed especially for this. You put blood in that, then the blood ends up separating into its components because the heavier parts go to the outside of the circle and the lighter parts don't go to the outside of the circle so much because the lighter parts don't have as much inertia. Yep.
That way, for some of the music part, right, you always want the heavier person outside, and everyone's pushing out the heavy person.
Could be. That would make sense, actually. I never really thought of that, but that would absolutely make sense. Yep.
I always thought something like that would have been really.
Yeah. No, I mean that could be. Yeah, I could see that. Where else have you seen a centrifuge? Well, you probably haven't seen a centrifuge like this, but you may have heard of it. Spinning a salad ball. That's a perfect example, actually. Perfect example. The salad goes to the outside. Well, what happens? The water goes even further, right? The water's heavier. Plus, the water fits through those holes a little bit better than the salad does. Um, they always talk about in the news, not so much lately, but over the last 5 years, quite a lot actually about North Korea, nuclear weapons, developing nuclear weapons. And sometimes you hear of this centrifuge. They develop a centrifuge. What's that for? Well, uranium, there's different isotopes of uranium, and it's one particular isotope of uranium that has to be used in nuclear weapons. But that isotope of uranium is not a commonly found isotope of uranium in nature. So for every 100 kilograms of uranium that you mine, there's like a kilogram of uranium or less that is this uranium that you want. So what you got to do is separate it. But uranium isotopes are chemically identical. So you can't use a chemical means to separate them. You have to use some other means to separate them. And one of the ways you can do that is with a centrifuge. The heavier isotopes, you spin it around enough, the heavier isotopes eventually separate and go to the outside. Now, it's a really slow process, and it takes a long time to get enough uranium for a bomb doing that. In fact, when the Americans dropped their bomb on Hiroshima in 1945, it took 3 years to get enough uranium for a single bomb that was never tested. It was never tested because they didn't have enough uranium to actually test it. They had to test it if they would have had to wait another 3 years to get more fuel to power it. So, centrifuge spins things around fast, separates components based on mass. The heavier ones go to the outside, the lighter ones not so much so. Here's our medical centrifuge separating blood into its parts. The centrifuge can spin up to 60,000 RPMs. What's its frequency in hertz, and what's the period? We're going to say frequency is 60,000 RPMs. How are you going to find what that is in RPS or in hertz? Let's divide it by 60. When you do that, I think you get I guess the answer is there, 1.0 times 10 to the 3 hertz. 1,000 rotations per second. You can imagine why this test tube has to be a specially designed test tube, right? And not just a regular chemistry Pyrex test tube. Now you want to find the period. We're going to say 1 over the frequency, 1 over 1,000, which is 1.0 times 10 to the negative 3. It makes one rotation in 1/1000th of a second. So it's going pretty quick, right? It has to be. If you want to separate the blood into its components, it has to be. You guys ever heard of a centrifuge in the context of like fighter pilot training or astronaut training? They spin astronauts around in centrifuges. And they do that to simulate G-force. The faster they go, the bigger the G-force, right? Pilots sitting there at 1G. It's fine. You experience 1G all the time, right? 2Gs, 3Gs, 4Gs. And when you start seeing them experience 4Gs, 5Gs, 6Gs, then they start, like their faces go back like this. And sometimes they start passing out, literally. Sometimes they just black out. G-lock, they'll call it. Why is that the case? Well, it's a centrifuge, right? It separates components of you. of the pilot. The blood goes to the feet. Well, if the blood goes to the feet, where's it coming from? The brain. What does blood carry that our brain needs? Oxygen. If you don't have any oxygen in your brain, what happens? Well, eventually you die, yeah. But you pass out first, right? So that's why you lose consciousness there. Let's do another example here. This one says a pebble is stuck in the treads of a tire at a distance of 36 centimeters from the axle. It takes 4.4 seconds for the wheel to make one revolution. It's the speed of the pebble at an instant. What do we got here? 36 centimeters. I'm going to circle centimeters, actually. Don't like that unit. What variable is that? Displacement? No. The pebble doesn't travel 36 centimeters, right? That's the radius of the circle. So we're going to say R is 0.360 meters. What's the 0.4 seconds? It's a time, obviously, right? But is it big T or little t? It's big T. It's the time for one complete revolution. And we want to find the speed here. So we're going to say V is equal to 2 pi R over T. 2 times pi times 0.360 divided by 0.40. When you do the math there, you end up getting 5.65 meters per second. Actually, it should be 2 digits, right? 5.7 meters per second. How could I add a twist to this to make it a little bit harder? Maybe I don't give you the period. Maybe we give you the frequency. If we give you the frequency, you'd have to find the period and then plug it into there. In this question, you don't have to do that, but obviously that's a possibility down the road. All right. Let's give these two questions a shot on page 251. I want to go over number 2 here. It says, in 2006, an Alberta astronomer discovered the fastest spinning collapsed star, it's called the pulsar, ever found. It has a radius of only 16.1 kilometers. So you think this is a star that has a radius which is the distance from about here to High River. That's a pretty small star, pretty dense star. And it's spinning unbelievably fast, 716 hertz, which is 716 rotations per second. So if you picture this, okay, if the middle of the circle is High River, and you're on the outside of the circle, and you're spinning around at 716 hertz, you're going to go from here, okay, all the way around, basically to Nanton, because that's about 16 kilometers on the other side of High River, right? And then back to here again, 716 times per second.
What?
That's how fast this thing is spinning. I mean, clearly you would not be able to withstand anywhere remotely close to that. All right, so we want to find the speed at its equator. We're going to say V is equal to 2 pi R over T. We've got R, it's 16,100 meters. We got to be in meters, right? And the period, we don't know. This is what I said in the example, right? Sometimes we might need to find frequency, we might need to find period from the frequency. So let's do that. Let's say T is equal to 1 over F. 1 over 716 gives me a period of what? 0.001. Keep going. Yeah, that's good. That's good enough. Now let's plug that into here, 0.0013966 seconds, and you end up getting a speed of 7.24 times 10 to the 7, okay, which is, I mean, that's unbelievably fast, right? The speed of light is 3 times 10 to the 8. Nothing can go faster than that. So you're starting to approach the speed of light here.